Welcome, all of you. This is SND College of Engineering and Research Center, Yeola, lecture series for first year engineering, engineering physics. I, Chaudhary Vivek Sitaram, from first year department. Today's topic is about types of laser. In that, we are seeing now gas lasers. Most widely used lasers and most varied, that is from low power helium neon laser to high power CO2 lasers, operated with rarefied gases as active medium, excited by electric discharge. There are neutral atom lasers just like helium neon laser, and some are ion lasers, argon ion lasers, krypton ion lasers, helium cadmium lasers, copper vapor laser, gold vapor laser. Now, some are also described as molecular laser, that is carbon dioxide laser. Carbon dioxide laser can also be nomenclature as gas laser, but it is particularly called as a molecular laser. There are again some types, that is excimer lasers. Excited rare gas dimers are embedded in that is argon, krypton, xenon, rarer gases mediums are there, and rare gases oxides, argon oxide, krypton oxide, and xenon oxide. So rare gas atoms in combination with halide atoms, that is argon fluoride, chromium fluoride, and xenon chloride. Chemical lasers are also there, hydrofluoride lasers. Now, schematic of gas lasers. In gases, energy levels of atoms involved in lasing action are well defined and narrow. Broad pump bands do not exist. Means whatever may be the lasing medium, in lasing medium, the lasing action have been done by the atoms. In this, atoms are excited. To excite gaseous atoms, pump sources with sharp wavelength are required, that is optical pumping, not suitable for gas lasers. Therefore, here discharge pumping is utilized, electric discharge is utilized. Most common method, that is passing electric discharge through the gas medium. So gas contained in a tube with cavity mirrors. The both sides of this cavity there are mirror. Rear mirror is 100% reflectivity, and the front mirror, that is from which we are getting output, is 99.99% reflectivity, means 0.01% transmittivity. A high DC voltage ionizes the gas for conduction. Electrons in the discharge transfer the energy to atoms in the gas by collision. Now, for optimum operation in practice, laser medium contains a mixture of two gases, just like A and B at low pressure. So atoms of kind A are initially excited by electron impact. They transfer their energy to atoms of kind B, which are actual active centers. So when we are considering helium neon laser, in this neon are the active centers. So helium are the materials which are getting impact of the discharge, and the cavity mirrors can be either inside the gas container or outside the gas container. If inside, the output light is generally unpolarized, but for outside case, mirror placed at Brewster's angle, that is polarized angles. Gas lasers vary widely in characteristics. Output wavelength from ultraviolet to far infrared region. Operates in pulsed mode and some in continuous wave modes. Output power less than milliwatt to tens of kilowatt. So first gas laser is helium neon in 1961 at Bell Telephone Lab, USA was invented. So first gas laser ever developed, still one of the most widely used laser, is helium neon laser. So helium neon, an atomic laser, employs 4-level pumping scheme. Active medium is a mixture of 10 parts of helium to 1 part of neon. Neon atoms are the active centers. have energy levels suitable for laser transition. Helium atoms help efficient excitation of neon atoms. So as shown in the figure, you can observe over here, that is, there is a discharge tube, there is one cathode and anode, and helium neon is mixture is fill up in that discharge tube, and both sides to this there is a mirror. One is rear mirror and one is the front mirror, and the output is 6328 angstrom unit, that is 6328 angstrom unit, that is in the red region. So discharge tube of about 30 centimeter long and 1.5 centimeter in diameter filled with the mixture of helium neon gas in the ratio of 10:1. So electrodes connected to high voltage, approximately 10 kilovolt, to produce discharge in gas. Now when high voltage discharge is applied, that ionizes the gas. Electrons and ions accelerated towards anode and cathode. Electrons, being smaller in mass, acquire higher velocity. So at the time of higher velocity, they transfer their kinetic energy to the helium atoms through inelastic collision. Helium atoms excited to level F2. Now as shown in the figure towards the right side, you can observe over here. When in the collision, excitation of collision with the electrons gets the atoms of the helium from the ground level to the F2 level. And when that F2 level collides with the neon gas, they transfer their energy to in the time of collision to the neon gas. Neon gas atoms get excited to the higher energy level. So when helium atoms excited to levels F2 and F3, that is metastable state, transfer energy to neon atoms through collision, resonant transfer of energy. So possible in helium neon atoms. Neon atoms, being heavy, could not pump up efficiently without helium atoms. Role of helium atoms to excite neon atoms and cause Pi. Probability to transfer energy from helium neon is more 10 helium per 1 neon atom. Reverse probability is small. So E4 to E6 level in neon metastable states, accumulation of atoms and population inversion. So now if you observe over here in this figure, what you will observe? You will observe that at the time of when helium transfer their energy to the neon atoms, at the time of collision, neon atoms get excited into the E6 level, and when from that E6 level they transfer with the transitive emission to the E5 level or E3 level. When if they are transmitted to the E3 level, they giving out 3.39 micrometer wavelength at the output, and if they are coming out from this stage to the lower stage, they are giving 6328, that is 6328 angstrom unit. And but if they are transferred from E4 level to the E3 level, they are giving out 1.15 micrometer wavelength. But from that E3 level, there is a spontaneous emission of 6000 angstrom unit to the E2 level, which is responsible for stimulated emission. And from E2 level, they de-excited by collision with the walls. The atoms of the neon get to the ground state energy level. So again population is achieved, and again population inversion is achieved by collision with the helium atoms. So if we observe over here, so if E6 to E3 transition, laser beam of red color, that is 6328 angstrom unit. If transition from E4 to E3 level, the wavelength is 11,500 angstrom unit. And if E6 to E5 transition, laser beam in the range of infrared, that is 33,900 angstrom unit. In reality, several laser transition, 150 possible, 150 transitions, level transitions possible. However, only 3 are dominant transitions. That's why we consider 3 level over here. Now, neon major applications as a So if we are observe E2 level is more likely to be populated by electric discharge itself. An increase in population at E2 causes decrease in Pi, so population inversion. So lasing ceases. Current in discharge tube maintain at low level, reason for not getting high power helium neon laser. So applications of this in the laboratories, in the interferometry, laser printing, barcode reader, scanners, surface testing, surveying and alignment, etc. Now we will see about the next laser, that is carbon dioxide laser. As in this level, it is also a molecular laser. In this we are using molecule of CO2 laser. That's why it is called as a molecular laser. One of the most powerful and efficient laser. A 4-level molecular laser operates on a set of vibrational rational transition. Output in the mid-infrared region at 10.6 micrometer and 9.4 micrometer. Both that is continuous wave and pulsed modes are possible. Continuous wave is greater than 100 kilowatt and pulsed we are getting energies as much as 10 kilojoule. So energy levels of CO2 molecules. Energy spectrum of molecules complex and includes many additional features. Each electron level associated with a number of vibrational levels. At each vibrational level, in turn, has a number of rotational levels. So CO2 molecule, linear molecule consisting of central carbon atom with 2 oxygen link, one on either side. As shown in the figure, so if we observe over here, in the center there is a carbon atom and 2 oxygen atoms are joined to each. So according to this, there are different vibrational modes. So there is a stretching mode, bending mode, asymmetric mode. So in the stretching modes, carbon is stable and oxygens can stretch to the either side. In bending mode, carbon is also oscillate to the upward downward direction and oxygen atoms are also bending just like you are exercising. And in asymmetric mode, one time carbon molecules is closer to the one oxygen atom, other time it is closer to the other oxygen atom. So each mode is quantized. Molecules can have 0, 1, 2 units of vibrational energy. At any one time, CO2 molecule can vibrate in any linear combination of 3 modes. At one time, CO2 molecule can vibrate in any linear combination of 3 modes. Each energy state presented by 3 quantum numbers m, n, q represent the amount of energy associated with each mode. So in this 0 to 0 means pure bending mode with 2 units of energy. Each vibrational state associated with rotational state corresponding to rotation of molecules about its center of mass. Much smaller energy separation between vibrational and rotational states. Now in this also, just like helium neon discharge tube, here also discharge is utilized. A discharge tube having bore of cross section 1.5 centimeter square and length of 25 centimeter. Tube filled with mixture of CO2, N2 and helium gases in 1:4:5 proportion. I repeat, the tube is filled with the mixture of CO2, N2 and helium, that is He, gases in the ratio of 1:4:5. Okay, so a high DC voltage causes an electric discharge to pass through the tube. Discharge breaks down CO2 molecule to O and CO. A small amount of water vapor added to gaseous mixture to regenerate CO2 gas. As shown in the figure, here you can observe where there is a cooling is required. So water is utilized for the cooling treatment, and here Brewster window. 2 Brewster window is utilized and 2 mirrors are utilized, and we are getting at the output the laser beam. Okay, in CO2 laser, N2 plays the same role as helium in HE laser. Lowest vibrational levels of N2 have nearly same energy as asymmetric mode of CO2. Readily transfer of energy by N2 to CO2 molecule in resonant collisions. So population inversion established between E5 and E4 levels and E3 levels. E4 and E3 are metastable states. In this, as shown in the figure, when nitrogen is excited due to discharge tube, they get excited and the energy of this nitrogen is transferred with the collision of carbon dioxide to the resultant in the carbon dioxide to the higher energy level. So that is, we get the population inversion, and from that population inversion, that atoms from the energy E5 may transfer to the E4 or E3 depending upon the size and that contribution. So we are getting the 10.6 micrometer if it is transferred from E5 to E4, 10.6 micrometer far infrared, and far infrared, that is from E5 to E3, 9.6 micrometer. So E5 to E4 transition at 10,600 nanometer and E5 to E3 transition 9,600 nanometer. CO2 molecules at E4 and E3 drops to E2 through inelastic collision. Here, after lasing action, they will drop their energy to the E2 level inelastic collision, and from this E2 level they are transferred to the ground state energy level by inelastic collision. So E2 level very close to the ground state tends to populate by thermal excitation necessary to keep the temperature of CO2 low. He has high thermal conductivity and conduct heat away to the walls and keeps CO2 cool. In CO2 laser, N2 helps to increase the population of upper laser level, whereas helium depopulates the lower laser level, available in different configurations, varying outputs. Applications of CO2. Applications of CO2 lasers are very large and huge applications, that is in industries and in research, in weapons, in military, that is for material processing, cutting, drilling, welding, etching, melting, annealing, hardening, and etc. So many tremendous applications over there, and in medical applications such as cutting and crushing, etc. So this can be utilized. So thank you very much.